According to the National Electrical Code, transformers over 600 volt amps must have a secondary overcurrent protection device, such as a breaker. The design in question does not meet National Electrical Code requirements because there is no secondary breaker installed. Without a secondary breaker, there is no protection against secondary overcurrents caused by short circuits or excessive loads. The transformer is rated for 2 kV amps. One load is protected by a breaker rated for 1/2 of the secondary full load amps, which is 10 amps for the 12 American wire gauge conductor and 7.5 amps for the 14 American wire gauge conductor. However, if both loads are operating at full load, the combined current draw would be 17.5 amps, exceeding the transformer's rating. To comply with National Electrical Code requirements and ensure the safe operation of the system, a secondary breaker should be installed in the transformer. The breaker should be rated for the maximum secondary current, which would be 17.5 amps in this case. The 12 American wire gauge conductor for the 10 amp breaker and the 14 American wire gauge conductor for the 7.5 amp breaker are appropriately sized for their respective loads. The conductor should be protected by conduit or other approved means to prevent physical damage and ensure proper grounding. The transformer and loads must be properly grounded to maintain electrical safety. To further elaborate on the potential violations and NEC requirements, let's delve deeper into the specifics of transformer protection and conductor sizing. The NEC provides detailed guidelines in Article 450 covering transformers. This article addresses various aspects of transformer installations, including overcurrent protection, grounding, and wiring methods. For a 2 kV amp transformer with a 208 volts primary and a 120 volts secondary, the primary full load current is calculated by dividing the volt amp rating by the primary voltage. That is 2000 volt amps divided by 208 volts, which equals approximately 9.62 amps. A 20 amp breaker on the primary side is acceptable, provided it meets the requirements outlined in NEC section 450.3. This section details the overcurrent protection requirements for transformers, specifying maximum overcurrent protection device ratings based on the transformer's impedance. On the secondary side, the full load current is calculated by dividing the volt amp rating by the secondary voltage. That is 2000 volt amps divided by 120 volts, which equals approximately 16.67 amps. The original design lacks a secondary main breaker, which is a direct violation of NEC requirements for transformers over 600 volt amps. The absence of a secondary breaker leaves the transformer vulnerable to overloads and short circuits, potentially leading to equipment failure or even fire hazards. NEC section 240.4 addresses the protection of conductors, stating that conductors must be protected against overcurrent in accordance with their ampacities. The 12 American wire gauge conductor, rated for 20 amps, is protected by a 10 amp breaker, and the 14 American wire gauge conductor, rated for 15 amps, is protected by a 7.5 amp breaker. While these individual branch circuits are protected, the transformer itself lacks overall secondary overcurrent protection. The NEC mandates that the overcurrent protection device must be sized to protect the transformer from overloads. In this case, a secondary breaker rated at or slightly above 16.67 amps is necessary to comply with code requirements. Installing a 20 amp breaker on the secondary side would provide adequate protection without nuisance tripping, provided the transformer's impedance allows for it. Grounding is another critical aspect of transformer installations. NEC Article 250 provides comprehensive guidelines on grounding and bonding. The transformer's metal enclosure and the equipment grounding conductors for both the primary and secondary circuits must be properly connected to ground. This ensures a low impedance path for fault current, allowing overcurrent protection devices to trip quickly and safely. The grounding electrode conductor should be sized according to NEC Table 250.66, based on the size of the derived phase conductors. In addition to overcurrent protection and grounding, proper wiring methods are essential for a safe and reliable installation. NEC Chapter 3 covers wiring methods and materials, providing guidance on conduit types, conductor installation, and installation practices. The conductors should be installed in conduit or other approved raceway to protect them from physical damage and environmental factors. The conduit should be properly supported and secured, and all connections should be made using approved fittings and connectors. Furthermore, it's crucial to consider the ambient temperature and dating factors when selecting conductors. NEC Table 310.15 specifies the ampacities of conductors based on their installation type and temperature rating. If the conductors are installed in an environment with elevated temperatures, their ampacities must be derated accordingly to prevent overheating. In summary, the original design violates NEC requirements by omitting a secondary overcurrent protection device for the 2 kV amp transformer. To rectify this, a secondary breaker rated at or slightly above the transformer's secondary full load current must be installed. Additionally, proper grounding and wiring methods must be followed to ensure a safe and code-compliant installation. Adhering to these guidelines will protect the transformer, conductors, and connected equipment from overloads and short circuits, minimizing the risk of electrical hazards. Remember to always consult the latest edition of the NEC and local electrical codes for specific requirements and regulations in your area. Engaging a qualified electrician is recommended to ensure that the installation is performed safely and correctly. Firstly, ensure compliance with NEC Section 450.3 regarding transformer overcurrent protection. This section dictates that transformers exceeding 600 volt amps must have overcurrent protection on both the primary and secondary sides. Secondly, calculate the transformer secondary full load current using the formula volt amps divided by volts. In this case, 2000 volt amps divided by 120 volts equals 16.67 amps. This is the maximum current the secondary can safely deliver. Thirdly, select a secondary breaker with a rating that does not exceed the calculated full load current. A standard 20 amp breaker may seem suitable, but careful consideration must be given to the transformer's impedance and potential inrush current. A breaker that is too large may not provide adequate protection against overloads. Fourthly, verify the ampacity of the conductors used on the secondary side. The 12 American wire gauge conductor has an ampacity of 20 amps, and the 14 American wire gauge conductor has an ampacity of 15 amps. These conductors are adequately sized for the 10 amp and 7.5 amp branch circuit breakers respectively. However, the overall secondary conductors from the transformer to the distribution point must be sized to handle the total calculated load of 16.67 amps. Fifthly, consider the impact of continuous loads on the transformer and conductors. If the loads are expected to operate continuously for 3 hours or more, the overcurrent protection device should be sized no greater than 80% of its rating. This is to prevent overheating and nuisance tripping. Sixthly, implement proper grounding techniques for the transformer and all connected equipment. Grounding ensures a low impedance path for fault currents, allowing overcurrent devices to quickly clear any faults. Refer to NEC Article 250 for detailed grounding requirements. Seventhly, use appropriate wiring methods and materials such as conduit or cable trays to protect the conductors from physical damage. Ensure that all connections are secure and properly insulated. Eighthly, label the transformer and all associated equipment clearly. Labeling helps to identify the components and their ratings, making it easier to troubleshoot and maintain the system. Ninthly, inspect the installation thoroughly before energizing the transformer. Verify that all connections are tight, all grounding conductors are properly connected, and all overcurrent protection devices are correctly sized. Tenthly, document the entire installation, including the transformer specifications, the conductor sizes, the overcurrent protection device ratings, and the grounding arrangements. This documentation will be valuable for future maintenance and troubleshooting. The design needs modification to comply with the NEC and ensure safety. The primary issue is the absence of a secondary overcurrent protection device for the transformer itself. While the individual branch circuits are protected, the transformer is vulnerable to overloads and short circuits on the secondary side. The recommendation is to install a secondary main breaker with a rating that matches or slightly exceeds the transformer's secondary full load current. This will provide the necessary overcurrent protection for the transformer and prevent it from being overloaded. Additionally, it's important to verify that all conductors are properly sized and protected and that the grounding system is adequate. Always consult the latest edition of the NEC and local electrical codes for specific requirements and regulations.